Now, the last integration technique, the first one we considered, was the substitution. The substitution is basically anti-chain rule. So we now are able to perform chain rule in differentiation and anti-chain rule or substitution in integration. The next rule we're going to consider is product rule, and therefore the opposite of it. So here I have the integral of x sine x. If I were to take the derivative of what's inside here, I would have to apply the product rule. So in order to figure out how to reverse the process, let's think about how the process works in the first place. So if I have a product of two functions, let's call them u and v, and I take a derivative of it, the product rule tells me that I have to take a derivative of the first times the second plus leave the first alone times the derivative of the second. Now, because the integration and differentiation are processes that are inverses of each other, what I'm now going to do is actually take integrals of both the left and the right-hand side here in order to think about what's going to happen to integration. Now, once again, because anti-differentiation and differentiation are processes that are opposite of each other, on the left-hand side, they will fully cancel, and I will simply get u times v. Now, I'm not actually going to be as lucky on the right-hand side because the insides here are not full derivatives of anything. Here, on the left-hand side, I get lucky because whatever was inside was taken a derivative of as a whole. So on the right-hand side, I'm simply going to still have integral of u prime v plus the integral of u v prime. Now, if I want to take an integral of a product of two things, then I actually want to solve this expression for one of the integrals, right? Because my eventual point is to actually be able to integrate. So let's solve it for one of them. It really doesn't matter which one you solve for, but it is standard to solve for this one. So if I isolate this integral, I'm going to have that u v prime is equal to, I'm going to isolate it on one side, then I'm going to have to move this integral over. So I'm going to get u times v minus the integral of v u prime. Notice that I actually rewrote this as such so that I have the primes as the second function here. And that is because there's another way to rewrite v prime the way that we've been writing it so far. This is the derivative of v, so dv. This is the derivative of u, so du. So I can write my full integrals here as u times dv equals to u times v minus the integral of v times du. And this formula is exactly what is known as integration by parts. Integration by parts is our next integration technique that we're going to consider, and it's going to be extremely useful in the variety of different integrals. It's also very nice because it's easy to recognize when to use integration by parts. It's used when the integral you have has two functions that have nothing in common. For example, here, one is a polynomial, one is a trigonometric function. There's nothing I can substitute for because the two functions are completely different in nature. And this is exactly why we would have had to apply product rule to them had we needed to actually differentiate. So the moment you have the integral that involves a product of two completely different types of function, this is when you call upon the integration by parts. Now, the setup of it, in order for us to evaluate it and use the formula, is a little bit specific. So let's go through that slowly to really see how the process works out. The first few, you're going to have to sort of trust in the process, and then we'll see how why that works out and how it goes. So let me pull up the formula here. It's u dv is equal to uv minus the integral of v du. So the first thing is we have to match the integral we have an integration by parts formula to the integral that we actually have, which means that we're going to decide amongst our product here what's going to be called u and what's going to be called dv. And yes, it does matter, but only after doing a few of these will you start recognizing what would work and what would not. So for the first one, what I'm going to do is simply assign an order. I'm going to call x u and I'm going to call sine x dx dv. Notice that I have to distribute everything in this integral to be represented as u dv. So I cannot just say that x is u and sine of x is dv and leave dx by itself. That's not a thing. Dx has to be a part of something. And then we're going to set up something similar to the substitution box, and this is just to keep track of the various components of the integration by parts. I'm going to record what is u, I'm going to record or figure out what is du, I'm going to record what is v, and I'm going to record what is dv. So I need all of these pieces of information so that then I can plug all of this back into my formula. So by just choosing what is u and dv here, I already have two things filled out in this table. I decided that my u is going to be x and my dv is going to be sine x dx. Excellent. Now I need to figure out what is du and what is v. Du is the derivative of u, so I'm going to take a derivative of what u is in terms of x. The derivative of x is dx. In order to go from dv back to v, I'm going to take the antiderivative, because of course what I'm given is actually a derivative. So in order to get the original function, I need an antiderivative of that. The antiderivative of sine x is minus cosine of x. So notice here, my du and dv have dx as a part of them. My u and v do not. That is because the second row here represents the actual derivative, whereas the top row here gives me the functions. Now let's plug all of this back into the formula. So the formula tells me it's u times v, so I'm going to read u and v from the table in terms of x. So this is going to be x times negative cos x, so negative x cos x, and then minus, so minus integral as per formula, v times du, so v times du. So I have here minus, well, let me actually keep this so that we can see where all of the minuses and pluses came from. So now I can simplify this expression a little bit. What do I have? Minus x cos x, and then I have minus minus, so plus integral of cosine x dx. Every time you do integration by parts, once you've performed the actual by parts part, you have to stop and ask yourself, is what you have now better than what you started with? So here, I didn't know how to take the integral of a product, but here, the integral that I end up with is not an integral of a product, it's simply an integral of cosine x, which I can of course take. So yes, this is absolutely better, because I can go ahead and actually perform the integration. I'm going to stay with my term here. I don't need to simplify it or do anything with it. And then the antiderivative of cosine of x is simply sine of x. So plus sine of x and plus the actual constant of integration. And this is it. This is now my answer. Notice that I can, as always, check this by differentiation. If I take the derivative of this, I should get back whatever was inside my original integral. So make sure that you actually trust that this is an answer, and you can in fact check that. Let's take a look at this next one here. What are we going to have? So this integral is very similar to the one above, except for instead of x, I have x squared. As I said, it's going to take a few different types of the integral in order to actually recognize what are the patterns that you're going to be seeing in integration by parts. But what happened here is when I allowed u to be x, this is exactly what brought this power down. This used to be x to the power 1, but taking the derivative of it got rid of x altogether. And this is why in the next integral, which was v times du, I no longer had the component of x because its power got reduced in the differentiation inside my integration by parts. So the idea here is if you have a polynomial, same as, for example, x squared here, it is beneficial to make that into u, because whatever you name to be u will get differentiated, and polynomials always reduce in power when differentiated. So that means that the next integral you see will have the same polynomial but to 1 power smaller. This is of course in sharp contrast to trigonometric functions that never go away or get simpler or get reduced. They simply bounce between sine and cosine with minuses and pluses alternating. So if you name in here sine to be your u, you will notice that in the next integral through the process, it would not have gotten simpler. You would have gotten basically the same type of integral back and therefore would have made no real progress whatsoever. So here too, I'm going to allow u to be x squared and sine x dx to be dv. And I'm in fact going to leave this for you to complete the integration by parts box 4 and see what happens. In this case, because you're starting with a quadratic function, going through the integration by parts will only reduce the quadratic function by 1. So that what you'll end up with is actually, in the process, the integral as above. But the good thing is that you can use the above integral because you know the answer, or you can use it to motivate your next integration by parts. So yes, sometimes you have to do it more than once. Let's take a look at other integrals that will involve integration by parts that are not immediately obvious. So here we have x ln x dx. So I again have two functions that are of completely different nature, polynomial and logarithmic, which immediately tells me that I am going to try integration by parts. So now, using our previous experience, note that whatever I call u, I will have to differentiate. Whatever I call dv, I will have to integrate. And I have to keep that in mind as I set up my box here. So u, du, v, dv. You might have to do this wrong, in a sense, a couple of times to really see what wrong means. And what does it really mean to not have it worked out? Until you see what a mistake looks like, you won't be able to tell what is actually a mistake. But again, u is what has to be then differentiated, and dv is what will have to be integrated right in the box as your first step. So this alone, actually with this integral, dictates the fact that I probably want u to be ln of x because I can differentiate ln of x, but I don't really know how to integrate this. Do you know the integral of ln of x off the top of your head? Is this one of the formulas that we have seen? Well, the answer is no, because the answer is actually non-trivial and in fact is our next question. So differentiating ln of x is something we can do quite simply. So let's try to see what would happen if we let u be ln of x. Now, if u is ln of x, then dv has to be x dx. So this will allow me to fill this out right away. And now I just have to compute the other two missing pieces of information. The derivative of ln of x is 1 over x dx. The antiderivative of x dx is of course x squared over 2. Now I have to take this and use this in the formula to see what I'm going to get. So first is u times v. So u times v, so I'm getting x squared over 2 times ln of x minus the integral of v du. Integral of v du. So the integral of x squared over 2 times 1 over x dx. Now I can simplify this to see if what I now have is better than what I used to have. So let me keep my first term as it were, minus, and what happens here is I can cancel out one of the x's and I can move 1/2 out to the front of the integral and I'm going to get x dx. Well, that's fantastic news because I most certainly can take the integral of x dx with no problem whatsoever. So what I'm going to get all together is x squared over 2 ln x minus 1/2 the antiderivative of x, which is x squared over 2, plus of course a constant. And we're done. So this was fairly straightforward, not at all painful. How about if we have something where I simply have ln of x dx? Now here, what I've been saying so far is that you're seeing two functions of completely different nature. Isn't quite right, because it doesn't seem like I have the other function. I only have ln of x. But it's not quite true, because I do have ln of x and I have dx. So this little dx allows me to work with that as a dv, and therefore really actually dig into this integral using integration by parts. So what's going to happen if I call ln u the same way I did here, and I call dx my dv? So let's set this up. If u is ln x, then I'm going to have to calculate du, and if dv is dx, then I'm going to have to calculate v. So taking the derivative of ln x, same as above, I'm going to have 1 over x dx. If dv is dx, what did I have to take a derivative of that ended up being dx? Well, that must have been just x by itself. So there we go. Now let's see what this gives us when we plug it back into the formula. The first part is u times v, so u times v, so x ln x minus the integral of v du, so x times 1 over x dx. Let's put those in and see what happens and if we can simplify this. 1 over x dx. Well, clearly I can simplify this quite a bit right away. Both x's cancel out. And what am I going to get? So I have x ln x from before the integral, and then my integral becomes that of 1 dx, which is really the simplest integral one can ask for. So x ln x minus, what is the antiderivative of 1? What would have given me 1 as an answer if I took a derivative of it? That's just x itself, plus of course the constant of integration. As always with integrals, you can take a derivative of this expression and you should get back whatever was inside your integral here. And if you don't, then you made a mistake. But this turns out to be true. The integral of ln x dx is x ln x minus x plus a constant. This much more complicated expression that one might expect is the antiderivative of ln x. And that is why you don't always see it as an actual formula stated by itself. Let's take a look at yet another integral that we will be attacking with the help of integration by parts. Here I have e to power x sine x. Very obviously two functions of completely different nature, exponential and trigonometric. So what can we do here? Again, let me just rewrite the same formula. U dv is equal to uv minus the integral of v du. And right away in the first step, I am faced with a dilemma of what I'm going to call my u and what I'm going to call my dv. Recall the earlier discussion about the fact that u needs to be differentiated, and therefore it might be a good idea to name something u that reduces with differentiation, whereas dv needs to be integrated, and therefore it needs to be something that you can actually integrate in the first place. Now here, if I let e to the x be u, that's not actually going to come down to be anything. The derivative of e to the x is always e to the x. On the other hand, if I let sine of x be u, the derivative of that is just cosine with a plus or a minus, right? So that's also never actually really going away or getting reduced. It seems like I'm going to be entering some sort of a cyclic pattern. So here, it doesn't seem like there's much of a difference what to call u and what to call dv. So let's just pick something and try. I'm going to pick e to the x to be u and the rest of the integral to be dv. So e to the x, the derivative of which is itself times dx, and dv is then sine x dx, antiderivative of which is minus cosine x. So what is going to happen if I plug all of that back into my integration by parts formula? I get uv, so u times v, or minus e to the x cosine x minus the integral of v du, which is minus cos x times e to the x. So this minus with this next minus will form a plus, e to the x cosine x dx. So we pause now and we ask ourselves, is this better? Well, no, not qualitatively, really. It's kind of the same integral, but instead of sine, we have cosine, which is sort of the same devil in disguise, right? The only reason it's better is that we just realized that by doing integration by parts, we can go between this integral and this one. So what we're gonna do is try to do it again. Now I know this seems like a little bit of a waste of time, but bear with me here. So what I'm gonna do is do the same thing. I'm going to call this guy u, and I'm gonna call this one dv, and try to see what will the second round of integration by parts produce as the expression. So u is e to the x, dv is cosine x dx, which means that my du is e to the x dx, and my v is sine x. Now let's replug it all back in. Now notice that this term has already been outside of the integral, so this term I simply rewrite, and the integration by parts will only be done on the actual integral remaining. So I have minus e to the x cosine x plus, and now we invoke our formula, u times v, so e to the x times sine x, e to the x sine x, minus the integral of v du, so v du, e to the x sine x dx. Now, is this better now? Well, I mean, depends on your outlook on the world, but I think it's quite a bit reasonable. What I have back is my original integral. So this isn't really going in circles, it's actually creating an equation that connects my original integral to itself. And the reason it's a reasonable thing to do is that because now I can use this equation to solve for my integral. In order to see better what it actually says, let me call this integral something. So let's say this guy, I'm going to call it I for integral. Okay, so this is also I. So what do I actually have? Let's rewrite the very beginning of this chain of equalities and the very last expression in it. So I have that my integral I was equal to these two terms in terms of the exponentials and trigonometric functions minus I itself. So what I have is I is equal to minus e to the x cosine x plus e to the x sine x minus I. How do I solve for I? Well, I can move this one over to the left, and then what I'm gonna have is 2i, because as it gets moved, the minus becomes a plus. So on the left, I'm gonna have 2i is equal to minus e to the x cosine x plus e to the x sine x. Great! I have expression for 2i. I can divide both sides by 2, and this is going to be the expression for I, and I is what I called my original integral, which means that that is, in fact, what my integral is equal to. So what I have from here is that my I, which is equal to my original integral, e to the x sine x dx, is in fact equal to, let me move this around a bit, seem to have run out of room, is equal to minus e to the x cos x plus ex sine x all over 2. And because I never quite did the integration explicitly, I never got a normal chance to introduce the constant of integration, so I'm going to do it right now at the very end. Isn't this nice? Yes, we had to do it twice on the same type of integral, but what happened in the end is that we managed to create an equation that connected our original integral to itself. And then once we created that equation, we could solve it for I as our original integral, resulting in this as the final answer. Now, this method is what we are going to use as the type of integration by parts you're doing if what you have inside are two functions that will have sort of cyclic or never-ending derivatives or integrals. Whether you take an integral or a derivative of e to the x, or whether you take the integral or derivative of trigonometric functions, but in particular sine of x, you're just going to be going back and forth to e to the x and sine or cosine with an alternating minus and plus. So there's just no other way. These functions are always related to the ones like them, so the only hope is to connect the original integral to itself in order to create an expression and then solve within it. Okay? Make sure you review this. This is the one method within the integration by parts that is usually just requires a little bit of getting used to, and this idea of being able to do something twice to come back to the original. Now let's take a look at an application within which we see a function that is requiring integration by parts. What we have here is the average concentration of a low-dose aspirin in bloodstream of a person when taken orally that is measured by this function. So what we have is a concentration, and notice the units here are micromoles per milliliter when T is measured in hours. We would like to compute and interpret the integral from 0 to 2 of this concentration being taken over time. So we're going from concentration to the integral, meaning we're actually computing the total amount of the drug that goes through the system in the 2 hours where we're computing it over. So let's take a look at how we would actually perform this integration itself. So I have 11.4 t e to the minus t dt. So now I am going to look inside my integral. This 11.4 is not a big deal. It's simply a constant that can be taken out. But what I have left is t, a polynomial, and e to the minus t, or an exponential, which means that I'm looking at two functions of very different nature, and therefore I will invoke integration by parts. One thing I have to be mindful of here is I actually have limits of integration. So this is something I'm going to, in fact, evaluate in between. So let's think about what our u and v are going to be, and let me quickly note the formula here so that we are mindful of what we're plugging in and how we're plugging it in. So now, again, this might require a little bit more practice before you can easily recognize which will be a good choice for you and which will be a good choice for v. But let's try to start with simply writing this down in a table. My choices are t and e to the negative t. Again, u gets differentiated, so if there's a function that gets reduced with a differentiation, then this is likely a good choice. Here we have a polynomial that most certainly will get reduced with a differentiation, and an exponential that never gets reduced. What I strongly recommend is for you to set this up with u being negative t fully to see what actually works. In fact, you know what? I'm actually going to do it right now. This really takes only one step to figure out that what's going to happen in this case will produce a worse integral. So if my dv is equal to t, then my v is t squared over 2. And this is what's going to appear in my integral once I go through and substitute all of these pieces into the integration by parts formula, which means that my next integral is going to now be t squared over 2 times du, which is going to be some sort of an exponential again. So I went from the integral that contained t and then exponential to the integral that contains t squared and then exponential. Definitely worse. This is the problem. When polynomials are differentiated, they get reduced. When they are integrated, they increase in power, and therefore your next integral is likely to be more complicated. Now, all of that talk just to persuade you that u should be t and dv should be e to the negative t dt. Then my du is dt, and my v, you got to be careful about the signs here, is minus e to the negative t because of the chain rule. So what am I going to have? As I mentioned, I can simply move 11.4 fully out and then compute within the formula. So u times v, so minus t e to the minus t minus the integral of v du. So v du, this minus and this minus will become a plus, and I'm going to have the integral of e to the negative t dt. Now remember that this all needs to still be evaluated between 0 and 2. And this is something you have to note right away here, because you already have a part of the formula that is outside of an integral, any integral. On the other hand, we still have this integral to compute, but this is much better because there is no factor of t here. This is a simple anti-differentiation, and this one I can perform no problem. So minus t e to the minus t, and the antiderivative of e to the negative t is simply minus e to the negative t. And this whole thing has to be evaluated between 0 and 2. Now, this is fairly straightforward. I simply plug in 2 everywhere, minus I simply plug in a 0 everywhere. So I'm going to leave these steps for you to complete. One thing I will point out about this exercise here and this function is that this 11.4 really needs to move out to be in front of everything, the entire formula that corresponds to integration by parts. So don't just accidentally attach it to the first portion and not the first one. These brackets here are really essential. Now, I really encourage you to take a look at this next handout, which comes from previous mistakes being made by students, and in particular on quizzes. So this first question here is giving you the different ways that people attempted to solve integrals and made some mistakes somewhere. Now, the mistakes that people usually make are really quite standard and quite normal in the learning process, so why not take this opportunity and learn from previous generations' mistake? Go through these and see how many mistakes you can spot, if you can spot all of them, if you can correct them, and identify what the student did wrong and why they might have been misled to do the thing that they did. Now, this is the same for the rest of this. Now, this is just a continuation of number 1. For number 2 here, this was an actual question on the quiz last year. This is a correct solution to the problem. However, it's not the most efficient one. Now, the efficiency, of course, is not a big deal. Correctness is more important, but efficiency might help you save time on an exam. And in general, you might be able to avoid some simple arithmetic mistakes if you introduce some efficiencies and therefore don't have to carry out similar calculations more than once. So take a look at this, figure out if you can do the exact same problem, but faster and a little bit more efficiently with a little fewer calculations on hand. This is really great practice for the tests.